Have you ever wondered where stars come from and how they form? Stars, those shimmering points of light that adorn our night sky, are born in the chilly, vast expanse of space. Their birthplace is in a nebula, a colossal cosmic cloud filled with gas and dust. These nebulae are the stellar nurseries of our universe, cradling the ingredients necessary for star formation. As if guided by an unseen hand, gravity begins to tug at every atom of gas and speck of dust within the nebula. Slowly, these particles start to clump together, pulled towards a common center by the relentless force of gravity. This gathering mass grows denser and hotter, eventually forming a protostar, the embryonic stage of a star. But the birth of a star isn't complete just yet. The protostar continues to grow, amassing more and more material from the surrounding nebula. As it does so, the pressure and temperature at its core escalate, creating a crucible for a process known as nuclear fusion. In this high-pressure, high-temperature environment, hydrogen atoms, the most abundant element in the universe, are forced together. They combine to form helium atoms, a process that releases an extraordinary amount of energy. This energy radiates outwards, causing the protostar to shine brightly, and so, a star is born. This process of nuclear fusion is the heart of a star, its very life source. It's what makes a star, allowing it to shine brightly in the endless night of space. It's a delicate balance though. The outward pressure of the energy produced by fusion is constantly battling the inward pull of gravity. As long as these two forces are in equilibrium, the star remains stable. So, it is the force of gravity and the process of nuclear fusion that give birth to a star. Each star we see in the night sky, from the smallest red dwarf to the largest supergiant, began its life in this way, born from a nebula and brought to life by the power of nuclear fusion. Now that we know how stars are born, let's delve into their lifespan. How does a star live its life? Imagine a star as a cosmic juggler, constantly balancing two immense forces, the inward pull of gravity and the outward push of fusion. This delicate equilibrium defines a star's main sequence phase, which is essentially its adult life. Gravity, the eternal cosmic sculptor, ceaselessly strives to compress the star to squeeze it into the smallest, tightest ball possible. But the star is not defenseless in this cosmic tussle. It fights back with the power of its core, where fusion occurs. In the heart of the star, temperatures and pressures reach unimaginable heights, igniting a nuclear fusion reaction. This reaction transforms hydrogen, the most abundant element in the universe, into helium. This process releases an incredible amount of energy, producing light and heat that we see and feel as sunlight. This energy pushes outward against the relentless inward pull of gravity. So, in the core of a star, a ceaseless tug of war is being played out between the forces of fusion and gravity. This balance, or hydrostatic equilibrium, is the secret to a star's longevity. How long can a star maintain this delicate balance, you ask? Well, that largely depends on the star's mass. A star like our Sun, of average size and mass, stays in this main sequence phase for about 10 billion years. But stars that are much larger burn through their hydrogen fuel at a faster rate. These massive stars may only last a few million years. On the other hand, smaller stars with less mass and thus less gravitational pressure burn their hydrogen fuel more slowly. These diminutive stars can stay in the main sequence phase for several billion years, outlasting even the most massive stars. So the size of the star determines how long it will stay in this main sequence phase, burning hydrogen into helium. This is a star's life, a cosmic dance of balance between the forces of gravity and fusion. As with all things, stars too must meet their end. But how does a star die? This question has fascinated astronomers and stargazers alike for centuries. A star's demise is not a simple matter. It's a complex process, a cosmic ballet of energy and matter that takes place over millions of years. The death of a star is dictated by its mass and begins when it exhausts its primary fuel source, hydrogen. Stars, like our Sun, spend most of their lives fusing hydrogen atoms into helium in a process known as nuclear fusion. This process releases a tremendous amount of energy, which keeps the star shining brightly and maintains its temperature. However, nothing lasts forever, and eventually, the star's hydrogen supply starts to dwindle. When this happens, the star begins to burn heavier elements such as helium, carbon, and oxygen. This shift in fuel leads to an increase in the star's temperature and causes it to expand dramatically, transforming it into a red giant or a supergiant. Our own sun will one day balloon into a red giant, growing so large that it will swallow Mercury, Venus, and perhaps even Earth. The star's fate after becoming a red giant or supergiant is entirely dependent on its mass. Stars with a mass similar to our sun will shed their outer layers, creating a beautiful cloud of gas and dust known as a planetary nebula. What remains of the star will collapse under its own gravity to form a white dwarf, a dense, hot stellar core that will slowly cool over billions of years. On the other hand, stars with a mass about 8 times or more than that of our sun meet a more dramatic end. These behemoths go out with a bang, in a colossal explosion known as a supernova. The force of the supernova is so great that it blows the star apart, scattering its elements across the universe. These elements, such as carbon, oxygen, and iron, are the building blocks of planets and life as we know it. But that's not the end of the story for these massive stars. The core that is left behind after the supernova can collapse further under its own gravity to form a neutron star, an incredibly dense object about the size of a city but with a mass greater than the sun. If the star was even more massive, the core could continue to collapse, forming a black hole, an object with gravity so strong that not even light can escape. So, the death of a star is not merely an end, but a transformation, a continuation of the cosmic cycle of birth, death, and rebirth. The elements a star scatters in its death throes will one day coalesce to form new stars, planets, and perhaps even life. Whether they end as a dramatic supernova or a mysterious black hole, stars certainly know how to make an exit. Even after their dramatic deaths, stars continue to influence the universe. But how? Let's delve into the celestial afterlife, the remnants left behind by stars after their grand finale. You see, stars are not just fiery bodies, they are cosmic factories. Throughout their lives, they engage in nuclear fusion, creating elements heavier than hydrogen and helium. When a star explodes as a supernova, these elements are scattered across space, sowing the seeds for new stars, planets, and possibly life. So, in a way, we owe our existence to the stars. The carbon in our cells, the iron in our blood, the calcium in our bones, all of it was once cooked up in the heart of a star. It's a humbling thought, isn't it? We are quite literally stardust. But the story doesn't end there. Depending on their mass, stars leave behind different remnants. Let's consider 3 of the most intriguing: white dwarfs, neutron stars, and black holes. White dwarfs are the remains of low to medium mass stars. They are incredibly dense, packing roughly the mass of our sun into a volume the size of Earth. They cool and fade over billions of years, eventually becoming black dwarfs, celestial ghosts haunting the universe. Neutron stars are the denser cousins of white dwarfs. They form when massive stars explode as supernovae, leaving behind a dense core. Neutron stars are so compact that a teaspoonful of their material would weigh about 1 billion tons. And then we have black holes, the remnants of the most massive stars. They are regions of space where gravity is so strong that nothing, not even light, can escape. They are cosmic monsters lurking in the darkness, their presence only known through their gravitational effects on nearby matter. So, from stardust to white dwarfs, neutron stars, and black holes, the afterlife of stars is as fascinating as their birth and life. Even in their afterlife, stars continue to play a vital role in shaping our universe. So, from birth to death and beyond, stars lead truly fascinating lives. They start their journey in the beautiful chaos of stellar nurseries, where clouds of gas and dust come together to form these celestial bodies. Throughout their lifespan, stars burn brightly, providing light and warmth to their surrounding planets. But even stars, with their incredible energy, have a lifespan and reach a dramatic end. Some meet their fate in supernova explosions, while others collapse into dense black holes, leaving behind a legacy that continues to influence the cosmos. The afterlife of stars is just as captivating, with remnants like neutron stars and white dwarfs continuing to puzzle and inspire us. Remember, every star you see in the night sky is at a different stage in this incredible cycle. So next time you look up, know that you're witnessing the life stories of countless stars. Don't forget to like, comment, and subscribe for more intriguing insights into our universe.